good morning, everyone. I apologize for the late start. This time I'm glad it's not my fault. I know I'm one who's always usually running a few minutes behind. But it's my distinct pleasure to introduce Amr Saleh for his thesis defense. Amr hails from Egypt. He did his bachelor's and master's degree in electronics at Cairo University, and then came to Stanford in, I think it was September of 2008.
Yeah.
So he's been at Stanford a while. He's quite the veteran. He spent his first 2 years working on microelectromechanical devices, and then came to me when I had first joined at Stanford in 2010 to say, oh, I want to work on something a little bit more practical. And I was able to convince him when he first started that working on Casimir forces was more practical than working on microelectromechanical devices. So back in the day, he sat outside my office and did derivations reading through quantum field theory and quantum electrodynamics. He did some really nice work in that area, and then finally came back to me and said, you know what, this has been a lot of fun, but I need something more practical. You know, so I read off and said, yeah, these aren't the most practical forces to work with. So then we started looking at coaxial structures, first because we were interested in making active optical devices like nanoscale lasers, active optical interconnects. Amr has a nice publication on that work. But kind of along the way, he started combining what he had learned with Casimir forces with some of the interesting effects he was seeing in coaxial structures. And we started working on optical trapping. So this is a project that Amr has been working on for about the past 2.5 to 3 years. I think it's pretty beautiful work that hopefully will lay the foundation for a variety of projects that Amr could take into his own independent career. While Amr has been at Stanford, he's won a few awards, including a Graduate Science and Technology Award from American University in Cairo, and Amr was also selected as a DARE Fellowship finalist. So without further ado, I give you Amr Saleh, who will tell us about the theory and some experiments on optical manipulation of nanoscale specimens with plasmonic tweezers.
Thank you. All right.
Shampoo is also on the way as a sixth
Okay.
member of the committee. So now you
Okay.
get extra.
Wow. All right. Good morning, everyone, and thank you so much for coming for such early defense. I'm really overwhelmed by your presence. So today, the essence of our talk is about how we can manipulate and control small objects with light. In fact, light interacts with different objects in various ways. For example, like this screen right now is one example like this. The light coming from the projector reflecting on the screen and to your eyes where you can see it. But there is another effect that is taking place right now, and that is the light coming from the projector is actually exerting force on that screen right now, and it's trying to push it. We can't really see this effect because it's very weak. So the first observation for such effect was done by Kepler in the 1600s, where he reported that the comet tails consistently points away from the sun as they circulate around the sun. And he even had proposed that this is because of like the solar breeze, what he called solar breeze. Right now we know that this is not like very wrong. It's actually true, more or less. And in 2010, the first space mission from the Japan Aerospace Agency utilized a large reflective solar sail to propel a small spaceship. And they used LCD cells to control the reflectivity of that sail to basically achieve the attitude control. So what is the origin of these optical forces? We know that electromagnetic waves from Maxwell's equations, we know that electromagnetic waves can carry momentum. So when light interacts with an object, for example, when it bounces off a mirror or when it refracts through a sphere like that, the momentum of the light changes. And we know that to maintain the conservation of momentum, the momentum of the object also has to change. So, and we know from Newton's law that any change in momentum is translated into a force acting on that object. And the first experimental observation for such effect was done over a century ago by Nichols and Hull, where they used a silver-coated glass vanes, like something like a fan, and they put it inside a vacuum jar on a torsion balance. And when they shined light on one of these vanes, they were able to detect the rotation of this vane. And they actually got very close results within 0.6% accuracy compared to the modeling of the radiation pressure. But the first real application for such effect was the optical tweezers that was reported in first time in 1986 by Ashkin. So the idea of the optical tweezer is basically to use, no, thank you. So the idea of the optical tweezers is basically to use a focused laser beam to trap a particle. So when this particle, when this sphere here feels the gradient of this focused laser beam, it experiences a force that tries to drag the particle toward the center of the beam, basically toward the maximum intensity of that beam. And there, the particle will be trapped, and we will be able to control and manipulate the particle. And since their introduction, there were a lot of applications, very important applications for such tool, especially in biology. For example, in this example here, optical tweezers were used to construct a three-dimensional cellular environments from the same cells and from different cells. This is very important because it allows us to study the functions of cells in different environments and with very high accuracy, because we can accurately construct certain structures of cells. So it's very accurate micro environments that we can typically create without optical tweezers. The other interesting application, or the other really cool application, happens actually inside the cells. We don't really know much about the dynamics that is happening inside the living cells. So for this example here, we see a kinesin motor, and these kinesin motors are very important in our cells because they basically transport the cellular cargoes from the center of the cell to closer to the membrane by walking over a microtubule. And we didn't really know what is the nature of this walking over this microtubule until the optical tweezers were used. So by attaching this kinesin motor to a large bead that can be trapped with an optical tweezer, and by monitoring how the kinesin motor, as it moves, as it walks along this microtubule, how it is pushing against the trapped particle, we were able to know that these kinesin motors walk in a discrete steps of 8 nanometer. So that gives you like an idea also about the precision of this technique. But there is a limitation for sure for this technique. And the trick here is that this image is actually not drawn to scale. If I were to draw it to scale to give you a perspective, it will look more like this. This is the bead, and the pixel here will be the kinesin motor. Why we do that? Because there is a size limitation. We can't really, these conventional optical tweezers cannot really trap cannot trap small particles. This is because as we get, when the particle is smaller than the wavelength, this gradient force becomes directly proportional to the third power of the radius, if we are talking about the sphere, and of course to the gradient of the electric field intensity. So when the particle gets smaller, for example, if this is a 500 nanometer and then we replace it with a 50 nanometer particle, this is a factor of 10, the gradient force will scale down by a factor of 1,000. So as the particle gets smaller and smaller, the forces becomes weaker and weaker. And these forces are important because this is basically what creates the trapping potential. Like the trapping potential is what confine the particle in space. So if these forces are weak, this trapping potential will not be able to confine the particle. So what is the criteria that we need to create a stable trapping potential? Well, we need this trapping potential to be larger than the thermal energy of the particle, or like larger than kT in principle. This is what we need. But if we want a more conservative estimation for the depth of the trapping potential, it would be 10 kT. And this is because sometimes there is an energetic molecule that can hit the particle and give it more energy than the kT, so it can easily escape from the trap. So to create a safety net, we make the trapping potential larger than kT. And using this limit, it was estimated that if we use a conventional optical tweezer that is just a focused laser beam, that is 1.4 watts, the smallest particle be able to trap will be between 20 and 12 nanometer. The other limitation with these conventional optical tweezers is the diffraction limit. basically we can't squeeze the light beyond half the wavelength of the light being used. So if we are talking about a laser beam that is 700 nanometer, for example, that means that the smallest spot we can create is about 350 nanometer. So if we are talking about a particle that is, say, 10 nanometer, then even if it is trapped inside this tweezer, it will be loosely trapped because it is trapped within a 350 nanometer. So this is another limitation. OK, so what do we need then to achieve the subwavelength trapping? We need two main things. First, we need strong field gradients at reasonable optical powers. Second, we need a subwavelength light confinement. And both of these requirements are met in the plasmonic modes, or the surface plasmons. These are electromagnetic modes that couple to the interface between a dielectric and a metal, and they are characterized mainly by the very strong field confinement at the interface between the dielectric and the metal, and also very strong field gradient from as you walk away from the interfaces. And the first implementation, or the first experiment that utilized this effect for optical trapping, it was gold nano antennas. So essentially what happens here, by utilizing the field enhancement in the gap between the two nanorods, it was the authors were able to trap a particle that is as small as 200 nanometer. And since then, there have been a lot of progress in this field. So a couple of years later, gold nanoholes were used to trap 50 nanometer polystyrene beads, and that is a factor of 4 enhancement. And then very recently, last year, there was another achievement that is to trap 20 nanometer particles. So this is another factor of 2 enhancement in this technique. But what we are going to propose today is that we can actually achieve a factor of 10 enhancement. We can trap, and so we will show that it is possible to trap particles as small as 2 nanometers. So this is another factor of 10. So why do we care? Why it's important to trap smaller particles? Basically, if we can do that, this enables us to explore new set of objects that we can't really access right now with the optical trapping. The size of like the green fluorescent proteins is between 4 by 2 nanometer approximately. A lot of nanocrystals are, or most of the nanocrystals sizes are between 10 nanometer and 2 nanometer. So we don't really have direct access to these whole families with the optical trapping. So this is why we want to break the limit of the 20 nanometer to the 2 nanometer limit. So the structure of the outline of my talk, first I will show you the design of the coaxial tweezers, how they work, and what kind of particles they can trap. Then I will show you how we can make them, how we characterize them, and I will share with you our recent results about how we can directly measure the optical forces at the aperture. And finally, I will show you how we can integrate those coaxial apertures on fiber tips and design an efficient optical three-dimensional optical trapping probe. So let's start with the first part. What is a coaxial aperture? So it's a simple geometry. It consists of a metal core, metal cladding, and a dielectric channel. So it's exactly the same structure of a coaxial TV cable. It's just like 100,000 times smaller. So those structures have had a lot of applications in the plasmonics field. For example, they were used to realize a plasmonic laser sources, and they were also, if arranged in arrays, they can make negative refractive index metamaterials. So let's first look at how they work, like how light can propagate along this coaxial waveguide. So we start basically, like as any standard electromagnetic problem, we solve the wave equation inside the structure, and we calculate the dispersion relation of that structure, that is calculating the propagation constant for every frequency. And this is the solution of the dispersion curve. And note that because of the azimuthal symmetry of the structure, it has to achieve periodic boundary condition along this angle phi. So that's why we get the factor e to the I nu phi, and this is why this structure can support multiple modes propagation. And here I'm plotting the first 3 modes, nu 0, nu 1, and nu 2. And the difference between these 2 modes is basically in how the field distributes itself inside the structure. So if you look at the field profile at this particular frequency, it will look like this for the first 3 order modes. And the most important thing that we notice here is that the field is mostly or like very strongly confined inside the dielectric channel with a very strong field gradient at the interfaces. Those are basically the 2 main things we need, the requirements for the optical trapping. And also when we look at the propagation constant for these waveguides, it's actually the light can propagate along these waveguides for a few microns. So this is also another nice feature for these coaxes at sub-wavelength. Okay, now how can we use these coaxial waveguides for optical trapping? So we consider a finite length of these waveguides. So here we are considering a finite coaxial waveguide that is 150 nanometer. And we did a dielectric channel of silica that is 25 nanometer and a silver core that is 120 nanometer. And the structure is illuminated from this side with a linearly polarized light. And the particle we want to trap is interacting with the field scattered from this waveguide. The first thing we do is we want to learn what is the optical properties of this aperture. So we do numerical simulation, and we calculate the transmission spectra of this waveguide. And we see that there are 2 peaks in the transmission spectra. And this is basically due to the fact that we are dealing with a finite waveguide right now. So that means that within this finite length, we can only fit certain wavelengths inside. And the wavelengths we are talking about are not the free space wavelengths. They are the plasmonic wavelengths. So whenever the plasmonic wavelength satisfies this condition that is twice the thickness, equal to or the same as the thickness, or T/2, and so on and so forth. Once this condition is met, we will be able to have a resonance. And this is a cross-section for these 2 peaks in the transmission. And you can see here we could fit lambda/2. Here we are fitting lambda. So this is basically what gives rise to these 2 peaks. And to double-check that, this is the dispersion relation for this excited mode. And this is the analytic solution for infinite waveguide, essentially. And we look at the 2 plasmonic wavelengths, 300 and 150, and verify that they are equivalent to the free space wavelength of 659 and 464. Very, very good agreement between what we get in our numerical simulation. So how can we calculate the forces on a particle interacting with a field scattered from this waveguide? We use Maxwell stress tensor formalism. And that formalism tells us if we can calculate the Maxwell stress tensor, this tensor T here, over a closed surface surrounding the box that we want to calculate the force on, we'll be able to fully determine all the optical forces on this particle. And Maxwell stress tensor can be fully evaluated if we know the electric and the magnetic field over this box. Once we have the forces, we'll be able to calculate the trapping potential that the particle will experience. So let's look at the performance, how this actually works. This is the electric field intensity profile, 20 nanometer above the aperture. And here we have a 10 nanometer particle. It will start to interact with the near field scattered from this aperture. So as the particle gets closer to the aperture, to the maximum intensity here, look at this force Fx. Fx is pointing in this direction toward this other door here. And so the particle will start to experience transverse force that is trying to pull the particle toward the center of the hotspot here. In the same time, there is another pulling force that is working toward the aperture. Basically, it's trying to pull the particle toward the aperture. So as the particle crosses at the other side of the hotspot, we see that the transverse force is flip sign, and now it's trying to restore the particle to the center. And at the same time here, the pulling force peaks right at the center of the hotspot. So this is basically the essence of how the forces that the particle will experience as it crosses over the aperture. We take the particle and scan the particle all over the aperture here, and we calculate the force field acting on that particle. So this is what we get. This is the force in the x direction, and it's consistently working to confine the particle to the center here, to the center of one of the 2 hotspots, and the Fy, basically in that direction, is trying also to confine the particle in the center. Combining these 2 forces, we can calculate the trapping potential that is trying to confine that particle. This is the trapping potential we get. So we get dual trapping potential, and the depth of that potential is as small as 20 or as large as 25 kT for every 100 milliwatt of output power. In the same time, in this plane, I'm showing you the pulling force that is trying to pull the particle toward the aperture where the potential is even stronger. And this force is quite large as well. It's about 6 piconewton. There is a very nice feature here as well. That is, with the plane wave, with a linearly polarized light, we could create 2 hotspots, and we could create dual trapping potential. So that means that if we can control the polarization, the direction of polarization, we can do further control on the particle. So let's see how this will look like. This is the field intensity cross section for this polarization, and this is the corresponding trapping potential. As we start to rotate the polarization illuminating the structure, the trapping potential will start to rotate as well. So this means that we have a tool that can apply some sort of a torque at the subwavelength in the very small particles. So this is also another great feature for that structure. Okay, we met the limit of the 10 kT. What about the diffraction limit? So let's take 2 cross sections along the 2 directions of this trapping potential. We see here that the full width at half max for this along the x-axis, it is about 46 nanometer, and along the y-axis, it will parallel to the y-axis, because this at x equals 67. The full width half max will be 96 nanometer. So we could beat the diffraction limit, and the particle is confined strongly inside this trapping potential. Now we want to know, okay, what is the limit? What is the size limit that we can trap with this design right now? So we consider 3 different sizes of particles, 15, 10, and 5, and calculate the trapping potential as the particle moves closer to the aperture. So for the 15 and for the 10, you can see here that they can easily meet the 10 kT condition right at the aperture. But for the 5, it still achieved this 10 kT limit. But once the particle moves further away, the trapping potential starts to decay quickly. So that means that the limit right now on this structure is 5 nanometer. Trapping smaller than that might be a little bit tight. So we want to improve this design. We want to achieve more. So we consider, okay, let's increase the gradient at the output. So we use the tapered channel, and right now the output of the coaxial, the thickness of the dielectric channel at the output of the coaxial is about 5 nanometer. So we repeat our calculations again, and this is the field intensity profile at the output, and this is 2 cross sections in the trapping potential on a 2 nanometer particle. So you can see here with this taper design with this channel thickness of 5 nanometer at the output, the trapping potential can be as deep as 60 kT. And the particle is really strongly confined. Here the full width half max is 8 nanometer, and here it's 40 nanometer. So with that, this is the take-home message of the first part of the talk. The coaxial plasmonic trapping enable the access of sub-10 nanometer particles. This is a new subset of particles that we couldn't really access before. And the particles are confined to a deeply subwavelength potential well, and the stable trapping potential can be achieved with low power budget. So we have achieved our goal from the first part of beating the diffraction limit and trapping particles that are as small as 2 nanometer. Now, how can we make those structures? How can we characterize them? This brings me to the second part of my talk. How can we make them? We used focused ion beam milling to pattern these apertures on gold films. And we can make arrays of them, or we can make individual structures. And as you can see here, this is a cross-section. The difference between the structure and the analysis that we have done before is that these structures now are air-filled because of the nature of the fabrication technique. And the first thing we want to look at here is the optical characteristics of these apertures. So we do the transmission measurement using a white light source and a condenser, and then we pick whatever is scattered from the aperture and send it to a spectrometer to look at the spectra. And this is what we get. Yes. And this is what we get. So you see here there is a resonance peak around 760 nanometer. So this is good, but is this what we really expect? Actually, to make sure that this is correct, we simulated the structure that we fabricated, and it showed this very good agreement between the two peaks, 760, both around 760. You notice here that there is some broadening in the actual fabricated device, and this is something to expect because of we know that because of the focused ion beam milling, the gallium ion doping in the channel will increase the losses. And also because of the rounding edges of the coax, this also will broaden the spectrum. Now we have another challenge. How can we actually probe the actual force acting on the particle? We can normally, in these trapping experiments, what you can do is basically monitor the particle and make sure that it is confined in space and report that it is trapped. But it doesn't tell you how much force this particle is actually experiencing. So we want to do that, or at least use a calibration standard from which we can map the force on any particle that we know. There are two main requirements we need to meet to achieve this goal. The first requirement is high spatial resolution. Remember that this aperture is a sub-wavelength. It's very small aperture, so we need a really high spatial resolution here. The other requirement is the high force sensitivity. We are talking about very small forces, piconewton and smaller. So we need a technique that can detect such small forces. So we started to think about atomic force microscopy. This is a rather simple technique. It relies on a tip on a cantilever, and as you scan a surface, the cantilever will start to bend up and down, and we have a very sensitive detection technique that can tell you the height of the tip as it scans over the surface. This technique has very high spatial resolution. In fact, it has atomic spatial resolution. For example, here it was used to reveal the atomic structure of the pentacene molecule. So it is literally atomic resolution. How about the force sensitivity? This technique, the AFM technique, was used to measure the attractive and the repulsive Casimir forces by detecting the deflection of an AFM tip as it gets closer to the surface of the sample. And as you can see here, it was like the range of the forces that it was able to detect was less than 100 piconewton. So this technique meets the two requirements we need for direct optical force measurement. So how can we use this in our experiment? Here's our coaxial aperture, and here's our AFM tip. When we illuminate the structure, the tip will interact with the near field forces, and it will be pulled down. If we are able to detect the deflection of the tip due to the light, we will be able to translate that directly into forces. This is our experimental setup. We have our sample here sitting on top of optical microscope, and the AFM head is integrated on the top of that optical microscope. And everything is stored in a hood, in a dedicated hood, to isolate everything from vibrations. And here we have our laser source. We take our laser into a mechanical chopper and feed the reference signal to a lock-in amplifier, couple that laser into an optical fiber inside the hood, where we couple it again to the optical microscope, and the sample is illuminated. And then we start to look at the deflection signal. And after processing between the AFM controller and the lock-in amplifier, we are able to read the tip deflection. So we start to try this experiment. First, we start to scan, find our structure. This is an example for a surface scan for one of our coaxes. And Now we locate where we want to measure our force. We move our tip to the point where we want to measure these forces. And then there's an important factor here in this force measurement, that is how high the tip is. We want the tip to be close to the location of where the particle is expected to exist. So we start to engage the tip until basically it is pushing against the sample, and where the deflection is 0, this is the sample. This is the surface sample. And then we start to retract the tip until we reach to the height, the targeted height we want to measure the force at. And basically dwell the tip and start to measure the forces. Let's see how this works. Now we are looking at the deflection signal. The laser is off. And then we turn on the laser, tip deflects, and the deflection signal changed. The first time we did that, we freaked out, so we turned the laser off and it went away. So that was a very exciting moment for us, because this was the first signature that we are able to detect a variation, detect the optical forces because of the AFM deflection. Once we have this deflection signal and we have the stiffness of the tip and the constants of the system, we are able to translate this deflection signal into a force. So this is an example of one of the measurements. Here, this is a transmission spectra, and we start the first illumination at 750 nanometer, and we measure the forces. And here's how the force is changing as we turn on and off the light, and you can tell how we're happy really with this toy turning on and off, measuring the force at the different moments. Then we change the wavelength to 620, and we measure the force again, and you see the difference because of the lower transmission through the aperture. So this tells us that we have a technique that can measure the force and can tell us also the spectral behavior of the force. Okay, but now we want to make sure what is the order of magnitude of the forces we are expecting in our AFM tip. So we run an approximate model for our AFM tip into our numerical simulation, and we can see here that the forces is in the order of a piconewton, which is something that we detected already. This is another example, and now let's look at the spectral force measurements. So the blue curve here, or the blue points here, are where we are measuring the forces at the different wavelengths. This is when the tip is right on top of the channel, and when we move away off the aperture, this is the background signal that we are measuring. So you can see the spectral, the difference and the signature of the spectral behavior of the coax. And if we compare this spectral force measurement to our transmission measurement, there is about 40 nanometer blue shift between the two curves. So that was something to think of. And then what we did is basically, okay, let's see how the coupling between the tip and the aperture can affect the transmission. So we did that, and now we are simulating the transmission spectra as the tip moves from one side of the aperture to the other side. And you can see here that there is a significant shift of 40 nanometer between the two as the tip crosses over the aperture. So the coupling between the tip and the aperture really affect the transmission spectra of the coax. So with that, let's see the take-home message of the second part. In this part, I showed you that that atomic force microscopy can be actually used to probe sub-wavelength optical forces, and that the forces, or the force resolution of this technique can be is in the piconewton scale. So we designed a structure, characterize it, but so far we have been dealing with planar samples. This means that we are only limited to the two-dimensional control of a particle. We are missing the third dimension here. We can provide this third dimension control by integrating the aperture on a fiber tip. And that brings me to the third part of my talk. So the first thing we consider, okay, let's try to simulate a coaxial aperture integrated directly on a fiber tip. And this is the dimensions of the typical coax that we can make using the focused ion beam. And here the diameter of this AFM tip is 5 microns, which is the typical core diameter of the optical fiber that works in the wavelength of interest. We put this design in the simulation, and we calculate the transmission spectra. So here you can see that the transmission efficiency of this design right now is rather low. It's like 2.5%. This means that this optical probe is an inefficient one. So what can we do to improve the transmission efficiency? Well, for plasmonic apertures, there was a trick that was used for nanoholes, that is integrating circular grating around the nanohole. And it was proved that this integration of circular nanoholes, if designed properly, the transmission efficiency can be improved significantly. So we are proposing to use the same idea on a fiber tip. Let's see how this works. This is our coaxial on a fiber tip, and these are the 4 main design parameters of the grating. Using our numerical simulation, we have 4-dimensional parameters to optimize over. So we do our optimization, and we look at how much improvement we could achieve. Here we have our aperture before integrating the grating. It is 2.5%. The efficiency is 2.5%. Once we have the grating included, the optimized grating included, this transmission efficiency is boosted up to 19.6%. This is a factor of 8 enhancement. This is associated with an increase in the field enhancement. You can compare the 2 field profiles with the optimized grating and with the no grating, and you can see how the difference is. And this is very interesting. This is very important for us because optical forces is directly proportional to the gradient and the field intensity. So this translates into enhancement in the optical forces. As you can see here, the blue particle is interacting with the coaxial aperture with the grating. The red particle is interacting with the coaxial aperture with no grating, and this is the transverse force trying to confine these 2 different particles, normalized to the same amount of input power, that is 50 milliwatts. And you can see the difference between the peak force here and the peak force here, that is again about a factor of 8. And this translates directly into the same enhancement in the trapping potential for the same amount of input power, 50 milliwatt. If we send 50 milliwatt for the structure with the grating, we can easily achieve the 10 kT required for the stable trapping. But for the 50, if we send the same amount of power in the structure without the grating, we can barely achieve the 1 kT. So this is a great enhancement in the efficiency. How can we make those apertures? We start with a lensed fiber that we cleave with a focused ion beam, and then we coat with a thin layer of chromium. Using focused ion beam, we start to introduce our rings to make our grating. Then we etch away the chromium, so we are left with bare glass that has the grating pattern. Then we do our gold coating, and finally we introduce the coaxial aperture right at the center, again using focused ion beam milling, and this is a cross section of this aperture. So you can see here, this is the input grating at the input side, and this is the output of the aperture here. Those probes, we design them, we make them, and the characterization and using them in actual experiment is an ongoing work. So that brings me to the take-home message of the third part. We have, with the optimized grading design, we can have we can improve the coaxial aperture transmission by a factor of 8, which will translate into same amount of enhancement in the trapping potential, in the optical trapping potential. And the successful fabrication of these optical fiber probes will enable the 3D manipulation of particles. So now we have a very nice technology in hand, the coaxial technology. What can we do with it in future? We don't want to stop at just trapping biological molecules, which is important, but there are another sets of molecules that we still want to trap and play with and analyze, and also we want to integrate that into an actual device that can be used in, so for example, in water purification. Here as this example, by using a landscape of coaxial arrays, it can, in the same time, it can achieve the parallel trapping of so many molecules, and if integrated in fluidic cells like that, it can be used for water purification, for example. The other thing, this is an ongoing work right now in our group, is that we show that if we truly engineer the illuminating light that is using circularly polarized light instead of the linear polarization, we can actually do selective trapping. We can distinguish between the right-handed molecules and the left-handed molecules. This is a very interesting technique because it has all sort of applications, especially in medicine and like in making drugs and such. With that, I will arrive to the conclusion of this talk. In this talk, I've shown you that coaxial apertures are powerful optical trapping. They conquer the limit, conquer another new area of particles, that is the sub-10 nanometer particles. I showed you how we can use atomic force microscope to detect piconewton scale optical forces and how we can measure the spectral force scattered from a sub-wavelength aperture. And finally, I showed you how we can integrate these coaxial aperture on a fiber tip to create high efficiency optical trapping probes. And that brings me to my most favorite part of any defense and probably the most important part, that is the acknowledgement section. So first of all, I'd like to thank all my committee members for taking the time to be here, especially for such early timing session. I really appreciate that from you. And I really particularly want to thank Mark and Shenhui, because before their nanophotonics class, the 336, I had no idea about photonics. It was my first exposure. And after that class, I was like, OK, this is what I want to do. And particularly, I want to thank Mark again, because I went to him and like, hey, I want to work in this plasmonics. I really like that. And he didn't have an opening. And then after a couple minutes thinking, he said, you know what? There is someone called Jen. She's starting in Stanford in 2 months. Why don't you contact her? Which I did, and turned out to be one of the greatest things that happened to me in the last 5 years. That is being the Jen student. Jen is really a great scientist, and her scientific insights and enthusiasm about science is really overwhelming. And I think in our group, we get all our energy to do science from her. Like she has some sort of a nuclear reactor that powers everyone in this group. So she is really amazing in science. But outside the lab, she's also amazing, like wonderful, wonderful friend. I really can't describe how great she is and how I'm grateful to be in her group. And I saw her. I was lucky enough to be among the 4 first students in this group. And I saw how she implanted the seed of happy, enthusiastic, scientific group that is this amazing group we have right now. I really thank you guys for all your support, for all the conversations, for all the feedback, everything, not just in the science, but also I have very beautiful memories with you outside. And this is just 2 examples of what we had. And these are memories that will remain forever, basically. I will never forget them. Outside from the D Lab, I'd like to thank the Islamic Society of Stanford University. This was basically my home outside the lab. There's no time to go over all the names. It's going to take another 45 minutes. But really, over the years, I made wonderful, wonderful friends. And every year, I know knew more people. And this has been my source of relief for the past 7 years. And I especially want to thank Waqas, who was basically he was the first person I ever met in the US. I didn't know him, but I emailed him, and he came to pick me from the airport. And that was the start of my journey here. And later on, my quals study group buddy, and then my roommate. So I want to thank him in particular. And smaller subset of this group is the Stanford Egyptians. Not that many, as you can tell. There's just a handful of them. But I really thank all of them, and particularly Ammar and Amr. At some points in this journey, there were really very tough time that I don't know how I could have gone through without their support. 3 people here, I couldn't find your pictures, so we should take more selfies. And I guess if anything, the reason like how I came here and the person I am is all due to my family. So if you don't like anything about me, those are the people to blame, basically. So particularly, yeah, I mean, as I go through life, I realize how much I learned from them. Yeah, sorry. And I particularly want to dedicate everything to my dad, who passed away last year. Yeah, that was a very difficult time. But I still find my joy, my happiest moments of the year when I go back, when I meet my brother and sister, and basically start a small fights with my 4 nephews here. And as they ignore me to play with the phone, and like I just start like, come on guys, let's play with real toys. And that brings me to the end of this acknowledgement section, because I can't really find words to thank them, because they are everything. Thank you. Thank you.